Familie ist, aber es mir. Einsteinian revolution.
And now you know about these things and my affiliation. So we move on to the core topic. This Newton's Principia came more than 300 years back, and it was one of the most beautiful theories, Newton's theory of gravitation. And Newton tried to form cosmology also. So Newtonian cosmology, what we envisaged is that infinite cosmos with uniform distribution of continuous matter. But then there is a problem. The problem is that the Poisson's equation Newtonian, if one applies for a sphere of say radius r, rb, then at the center this is the potential one gets. And if rb goes to infinity, the center becomes infinite, then apparently Newtonian gravitation gives infinite negative potential. So this is one of the main objections to puzzles for Newtonian gravitation, and this was not solved. Apparently this was solved only after Einstein came, formulated without general relativity, and this is a new kind of theory. Again, it describes matter only in terms of continuous distribution of energy momentum. This is a revolutionary concept. In 1917, next year Einstein applied his theory for the structure of the cosmos. So, and he found what is now known as Einstein's static universe. So he found a universe. It is on a three-sphere. What is a three-sphere? We know the surface of a balloon. It is a two-sphere. It is some sort of mathematical abstraction. It is sort of a balloon surface, but in a three-dimensional surface. And apparently that things could be very finite, nice, and confined. But even when applies a general relativity initially, Einstein get for a static distribution matter density 0. So at this stage, he made a hypothesis, cosmological constant, something repulsive gravity in the membrane of the space-time. So everywhere some repulsive gravity is there, and then apparently one gets a finite density. The Einstein finite density rho was related to lambda. Rho is lambda over 4 pi. Here I have taken g and c natural units. G and c is unity. And the radius of the universe, one can so to say this parameter is given by this relation. This was Einstein's static universe. And at the same time, Sleeper was detecting, they are doing observational cosmology those days, and they found, and finally Hubble, many redshifted galaxies, distant galaxies redshifted, spectral lines from distant galaxies are redshifted. And simultaneously, meanwhile, De Sitter did very important work. He found a solution, that cosmological solution, there is no matter at all, but only this repulsive cosmological constant, and matter is 0. And this came to be known later. Einstein in 1922, Friedman had found solution for expanding universe solution. And 1927, Lemaitre did. It was first in this Danish journal. Later, Eddington translated them, and this was the two papers. And that really gave the first concept of expanding universe in a more mathematical form. And Lemaitre there assumed that universe is born from some primeval atom. Now, when you have this expanding universe kind of thing, then you have this kind of relationship. Here S is called the scale factor, and these 2 over 2 means double derivative with respect to cosmic time, and in this model there is a universal time like a Newtonian time. Then pressure is 0, and in Big Bang you have no collision. By definition, any observer sees everything else nicely moving out in a radial fashion, and this is by Weil postulate, there is no collision. That is the reason intrinsically this pressure is 0. Then you have temperature.